So we're now on to part 222, line 19, a2b, circular linear polarization target detection, Quanta Hadrons, 5G Wow Seti. There's your Wow Seti signal, and those are the numbers we're going to Google. And then May 14, 2012, 10:26 a.m. We're going to Google electron wave interference from line 19A2A. This keyword comes up, circular detection probability, and then this thing comes up here, wherever that is, a URL, PDF. We got another PDF here from May 1988. This paper describes an algorithm for calculating circular error probability. Now, if I'm not correct, I'm going to take a wild guess here. For circular error probability, that usually deals with missiles or things that like rotate. And since we're trying to create a rotating UFO engine body thing here, this obviously is very important. So the CEP, which is frequently used with target location estimates, CEP relates measurement errors to the variation of a calculation that is computed from those measurements. Mathematical foundation is provided for the CEP estimate, and the algorithm is shown to be extremely accurate. So obviously they want you to use this algorithm for whatever it is you're going to make. So it differs from the true CEP estimate by less than 1% on average and has a maximum error of 1.5%. As such, it is useful tools for assessing both the accuracy and sensitivity of any calculated quantity to errated input. Descriptors: position, location, circular error, probable algorithms, measurement, accuracy, estimates, errors, mathematics, target detection. There we go. How did I know? So it's fire control and bombing systems, approved for public release. So obviously it's got something to do with some sort of missile thing. So this is Journal of Applied Statistics, 1993, measuring the probability of patch detection for forest spatial sampling designs. This came up with the search from John Barry and Mike Nicholson, July 2006. In this paper, we derived the probabilities that 4 chosen sampling schemes will detect a circular patch of organisms whose location is at some random location in the study area. We also describe simulations which indicate the variation of patch detection probabilities for different realizations of the sampling design. We comment briefly on how probabilities would be affected by multiple and different shaped patches. Our results are a useful guide for practitioners when choosing a design and an appropriate sampling intensity. And it's from www.tandfonline.com. Next is the Zeitschrift for Zeke, Hadrons and Nucleons. Looks like it's German or something. Either German or Russian. Something came up here from G. Schmidt and L.M. Simmons, so I'm saying it's German. Observation of the circular polarization correlation of the positron-electron annihilation quanta. So the abstract is the circular polarization. Okay, that's done twice. The circular polarization, angular correlation of annihilation quanta has been measured unambiguously by use of 2 backscattering Compton polarimeters in coincidence. The interpretation of the measurement required a quantum mechanical calculation of the circular polarization detection probability for coincident annihilation quanta. This calculation showed that the most favorable geometry for detecting a circular polarization correlation is the backscattering geometry, because here, in contrast to forward scattering and transmission geometry, strong perturbations by the linear polarization correlation are not present. By using the polarization efficiency N equals 4.7% for a single polar meter, which was derived from a Monte Carlo calculation, the measured effect for the circular polarization correlation, okay, that's the name of it, showed good agreement with theory. No, I was just wondering why I was repeating there twice, sorry. We wish to thank Professor E. Bodenstick for his constant interest and kind support, and Professor J.K. Beanlin, who suggested this experiment. The calculations were performed on the computer of the GM Bond The experiment was financially supported by the Bundesminister für Forschung und Technologie, and it's from www.springerlink.com. Go to our next video now.